All right, so beginning our lecture on Chapter 9, the Moon and Mercury. The plan for this chapter and for these slides is to talk about the moon, its surface, its origin, a little bit about its exploration, which I'll move through quickly, and a bit about its tidal lock to Earth, which, although we talked a lot about phases, we've never explicitly described the tidal locking of the moon. Then we'll move on to discuss Mercury, its key features, and in fact, in the same format as we describe the key features of Earth, which means that this will be our second planet in our catalog of planets. But as we go through all 8 of them, we'll talk about the composition. So, of course, that's the interior of the planet, its crust, its surface, including some surface features, and a bit about its atmosphere, which, yeah, it kind of has one, but it's really thin. Where with the moon, really, we can say it doesn't have any atmosphere at all. It's basically just pure vacuum of space around the moon. So, talking about the moon. So, the lunar surface has a number of basically features with specific names. And those are the catenas, craters, the highlands, the maria, moon dust, and the riles. Okay? And to group together some of these different named surface features, we can consider those created by geology. So things that features that are created because of something that happened inside of the moon, often early in the moon's history, and features that are created by space. So features that are created because of some direct influence from outer space. Well, starting with the highlands, right, which we can see are created by geology. They are light-colored, hilly raised regions. Their light color relates to the light silicates that have floated to the surface. So that is referring to the differentiation of the moon because, yes, it's differentiated as we should suspect or expect since it's, a round body. All right. And that differentiation occurred when the moon was molten. The maria are flat, dark areas formed from lava flows. So we got light, highly reflective areas, and then we have darker lava flows that have fewer craters. Okay, so the flatness has a lot to do with the lack of cratering on the maria. And it's not an absolute lack, it's just a dramatic difference. There's about 10 times the craters per square kilometer on the highlands than on the Maria. All right, and this is showing both together. I thought this one had some labels on it, but it's showing, a big Maria right here. This is the side of the moon that we can see from Earth, by the way. And, so we can see this darker, big lava flow region. One distinctive crater, obviously a few others as well. All these little light spots are craters, but not many. And that's filling in this whole region, but then around it are highlands, right? Almost a peninsula of highlands over here, and then the whole upper, latitudes of the northern hemisphere of the moon are highlands, no major maria, although some, right? And these are kind of like partial ones, but they are, right? And then a really distinctive big maria here, all right? And a crater right on top of it. So that's a later crater. If you've done some reading and seen about where the Maria fit into the history of the moon, you know that they came later. And so to see a big crater on top of the Maria tells us that this was some almost like, the asteroid that wiped out the dinosaurs, right? Some sort of a rare event that happened relatively recently. When we talk about the aging, all right, and we compare which is older, all right, well, I kind of just gave it away, but in case you weren't listening, or maybe it wasn't entirely clear, which is older, the Highlands or the Maria? Go ahead and tell me. Ah, I told you. Whoops. I don't know how I did that. Yeah, thank you for still answering, Maria and Maxwell. Yeah, you're already typing it. Yep. The highlands are older. It's an older surface. So there was something underneath the Maria, basically what would have been, more highlands, but they got covered. Also, the Maria kind of filled in big craters. Sometimes that's really obvious if you look. So you can like see cases where obviously there's some sort of ancient crater on the moon, and then it got filled in by the lava flow that is the Maria. So the Maria are these big lava flows that happened more recently. Now, let me show you the one I'm thinking of. Like right here. This is like just filling in that big crater. Okay, so this time I do actually want you to answer, and I won't proceed by accident. An altimeter is placed in orbit around the moon. It uses radio waves to track the elevation changes on the moon's surface below it. Which of the plots below correctly show the elevation of highlands and Maria? So you got four options. Look at the information it's showing you. And it's kind of like purposely vague about like what you're supposed to look for, but just look at them and there should be something that jumps out at you. Look at the four different plots. Let's get another answer or two. Thank you, Maxwell and Maria. Both in agreement again. Let's see. Yes, indeed. And I'm guessing that you knew because the highlands were both higher, right? Which would narrow down the options between one and three, but three had the highlands bumpy and the Maria flat, where one had that reversed, which was incorrect. All right. So all this small scale elevation variation in the highlands is because of all that cratering. Yeah, you got 100% so far. This was a quiz, right? You'd be doing great. Okay. But, do great at quizzes anyway. You all do. I mean, yeah, I'm entering those quiz scores, a lot of high scores. So more lunar surfaces. Okay, so the Riles are less well known. I always find myself talking about the Maria. Riles don't come up as much. You may see a question or two on them, so we'll quickly cover what they are. They're just these long, straight features. They actually are caused by a at least a few distinct different phenomenon. All right. So, but what they all share in common is that they are long, thin ditches along the surface. They're actually not always straight, but they're just a long ditch. So like a canyon, right? But not a canyon because they're not steep enough to be a canyon. So they actually look more like a ditch. But of course, you think ditch, you might think man-made. These aren't. These are naturally occurring. The name of one, Rima Cauchy, and they all seem to have Rima in their names. So it's almost like the feature's called a Ryle, but the naming has Rima. I don't think it's a plural and singular thing, just kind of a variation in the name. But it's a straight Ryle that's formed by the surface pulling apart and the ground sinking down into the gap. So that on Earth, actually, there's a feature called a graben, which is the same thing, where the surface is just pulled apart, and that it can happen from a number of things. In the case of Death Valley, it's kind of because of the fault line, and that strike slip fault line and sort of some deformation in the plate. Um, these could have happened early on in the history of the moon, so during some sort of cooling process and formation of the moon, but also more recently, right, from like a really disruptive impact or from some of that volcanic activity that led to the Maria, and you got like a increase in density on one part of the surface, right, kind of causing it to like buckle, and then you could have these resulting sort of stretches show up, some kilometers away. And I'm sure people look into these things, but we're not worried about the exact mechanisms, other that it was a stretch. Here's another Ryle that looks like a riverbed, right? But it's definitely not. There's never any flowing water on the moon. That's in contrast when we talk about Mars and we see features that do actually show the past flow of water. This is not one of those. This one's called Rima Sharp. It's funny, right? Because it's actually, it's so sinuous, and serpentine, but it's called Sharp because it's named after someone whose last name was Sharp. And it'd be classified as a sinuous ryle, right? Rather than a straight one. And this one was formed by flowing lava and perhaps like a lava tube that collapsed, right? So, like underground, melting through the surface, and then later collapsing as everything cooled. One more ryle, right? This one, a long, thin ditch stretching across the surface. This one is a arcuate ryle and formed by heavy lava collapsing as it cooled along the edge of Maria, of a Maria. So also a lava flow feature. That's what the last two had in common. Okay. So then there are catenas, and catenas are a feature that's created by space. So direct influence from space, not a geological feature, and they happen. All they are, they look sort of fascinating and different, but all they are just a series of craters. But it's not just luck that a bunch of craters lined up like this. It's actually when a single asteroid or comet broke apart, and then when it hit, it hit in such a way where there's all those separate pieces like following a path downwards, and hitting like one after the other, thus creating this long line, almost like a really like stretched out oblong shape, but just also just like a series of overlapping circles. It reminds me of playing Angry Birds with the blue bird that splits into three individual birds. Um, if you ever played that game. All right. So, as we say, we can point out lines of craters. This is cheating though, because this actually isn't the moon. I guess that they couldn't find a good example. There are catenas on the moon, but this one is on the moon Ganymede, which is a moon around Jupiter. But it's such a good representation of a perfect catena. Although I should look up one that actually is the moon. Okay, so then there's the regolith, which is kind of weird to group in. This is the moon dust, um, which is how it was listed originally, because we've been talking about these big features. This is more like, on the small scale, what the surface is made out of. But what it is it covers the whole surface of the moon, and it's just this pulverized rock that makes this really fine dust. And we don't really have anything like it on Earth. There are some deserts that have some strange types of really fine dust, rather than the typical sand grains. But that's more just because of what type of minerals were exposed to erosion, with wind and water and so on. But this isn't, right. There's no atmosphere. There never was erosion. We don't see like volcanic rocks except on the Maria. So it's just this strange case where it's just hundreds and millions of years, billions of years of impacts from space. And the result is just everything has just been broken up into little pieces. And there's never been anything else going on, right? There's never been any processes to compact this dust down. There's not tectonics. There's no, like I said, there's no watersheds. And so everything just leads to the dust just getting finer and finer over time. And so that's why it just covers the surface almost uniformly. There are bigger rocks kind of like throughout it, but between all of those boulders and larger rocks is regolith everywhere. And Mars is like that too, and the same term is used. So like Mars is covered in that same fine dust. It's really an impediment to exploration and human habitation. Even in like just for on bases, like not like moving to Mars to grow a civilization there, but just even just like have a permanent base on Mars. That the regolith is just like it's super harmful. It gets into everything. It's hard to filter out. It's just sounds like a real pain in the butt. And then, of course, craters, which are just your iconic result of an impact from space. They're just big bowls made by objects, right, hitting the surface, right, impacting the body being the moon. When we talk about crater creation, the crater hits. I need to fix this because there's missing images. I'm not sure why. But there's impact, vaporization, ejection, and then the all that vaporized material. we're talking about the regolith, right? That fine dust. A lot of it settles back down and fills in the crater. So the crater is not nearly as deep as it is right after the impact. Um, but the vaporization is kind of interesting because it explains why almost all craters are circular. Because, meteorites can hit, or meteors, can come in, right? The path of a meteor can come in at a steep angle, but yet we don't see like these stretched out craters. And compare that to like if you're throwing like a rock into a sandbox, right? The sandbox is the stand-in for the moon's regolith, and focusing on the moon here. If I throw a rock into a sandbox, if I throw it so that that rock comes in at a really steep angle, just a couple of degrees above the horizontal, it's going to create like this big like streak, right? It's going to like push the sand in front of it, and it's just going to be this big big long streak mark with like a rim at the end of it. Okay, well, if I instead drop the rock from straight above, then I would get this circular indentation that would kind of look like a crater. All right, but that circular one actually wouldn't be a crater, and the other one, the long streak mark, also couldn't happen in the case of a meteor coming in or a asteroid, vaporizing and hitting the surface because the vaporization. The thing is that with the rock didn't vaporize, right? It just hit the sand and pushed the sand out of the way. And so in both cases, the rock would still have been there. And if I wanted to, see the crater looking indentation when I drop the rock from straight above, I'd have to remove the rock. And so that's the key difference is that when these meteors come in and they hit the ground, they hit with so much energy, they almost nothing's left. Yeah, there are meteorites. We talk about that on Earth, and there's plenty on the moon as well, but they're just little fragments. Most of that rock and metal turned into vapor. It phase changed. It just completely blew up. And because that impact is driven by the vaporization, it makes it symmetric, no matter what angle it comes in at. Because the vast majority of the energy being released is not just the kinetic energy of the moving object, but all the energy associated with the bonds that made something solid that are getting broken as it's getting vaporized. Well, that's what creates that symmetric crater. So, kind of interesting thing that it is easy to overlook until you find yourself wondering why all craters are circular. In terms of crater features, they've got the floor. You kind of that sounds like what it is, big flat part at the bottom of the crater. The walls where it starts to increase in elevation. The rim is just the name given to the very edge of the crater. That's the high point. So we want to be able to define that so we can define rim height and so on. The central peak is an interesting feature that has to do with the refill. So the refill happens in such a way that there's always going to be more of it settling straight down. So you end up with a little, piling right in the middle. More dust is going to find its way back down to the middle. The ejecta are the sides that come down off of the rim where all the pieces were blown away and also settled back down after taking their paths through the air. And the rays are just extensions of the ejecta, and we can see a better picture of them. There, you can see six, and it's kind of hard to tell what it's pointing to compared to five. Other than that, there seems to be some longer kind of tendrils coming out, but we'll see a better ejecta in a second. What's interesting is that the peaks, that which is you can see, you can see the shadow of it, right? And this is just a pile of loose regolith. When you see pictures of them, they actually kind of look like mountains, right? Like you'd imagine from like geological processes. But these are just the peaks of craters. And when they look like this, it's probably from a really big crater, right? So some of these craters are huge, tens of kilometers across. And so that's can create a pretty large central peak. And so it's not a mountain, it's just settling of loose dust. And I'd imagine if you tried to, walk across it in your lunar spacesuit, it'd be like trying to walk up a big hill of loose dust. It would just be crumbling under your feet. And then the rays, you can see in this large crater are these like kind of white lines that permeate outwards. And again, in in the trend of showing images that aren't actually the moon. This one is showing a crater on Mercury, but at least we're talking about Mercury in this set of slides. So there's that. But what I'm mousing over right now is a ray as it extends outwards. And so, so there's almost like there's like total coverage close by in terms of the ejecta and the debris that's settling. But as you get further out, it becomes, concentrated into these rays. And it's just, it just has to do kind of with the blast pattern and the way things are spreading out. Now, craters create the shadows, and they can be quite deep sometimes. And depending on where they're located on the moon, these shadows can have real important consequences. Okay, so crater shadows. On the one hand, of course they create shadows. Why do we care? Well, let's see. Okay, so let's consider a crater. All right. So you got, the shadow inside the crater. What's the cause of the shadow? The cause is the path of the sunlight. Because here we've got the sun. The sun is not at the zenith of, this terrain, right? So an observer on the surface of the moon here, standing in the crater or anywhere around it, would not see the sun at their zenith. And the reason for that is because presumably this crater is not at the equator of the moon. So the sun would never pass through the local zenith. And to really kind of drive that idea home, the moon doesn't have any axial tilt, or approximately zero. So that means that the latitude is equivalent to the altitude of the sun on every day of the year. Okay. Now, lunar days are long, they're like 13 Earth days, but every latitude you're at relative to the equator of the moon, the sun will reach the same point in the sky on each lunar day every single day. And I got how many, like how many days, it's not the lunar, there's not like a lunar year, right? But there's a certain number of days in, an Earth year, which I guess would be about, because there's about 2 lunar days in or well, a full day, because the night when I said 13 days, I just meant like that's the number of hours of light, but the full day is a month. And so then, let's say 29 days, right? So you've got 29 days, so which I know doesn't divide into 13. I could have said 14 and a half, I suppose. So, 29 days for a lunar day. Well, yeah, that's so you got about 12, right? 12 lunar days per Earth year. And so that's kind of, that's your breakdown. But all that aside, I just want to make sure that that was, kind of like you weren't like finding yourself distracted by thinking about what is a lunar day. But every time, on these long lunar days, the sun just would always reach the same point. There's no variation throughout any period because there's no axial tilt. And, that means that if you're at a high latitude, then the sun never reaches a very high altitude remember that the equivalence that I was talking about isn't the angle that's measured relative to the horizontal, but instead it's the angle that's measured relative to the vertical. So it's gonna kind of have to squeeze in, but if I draw a line that represents the direction towards the zenith, just the vertical line, then this right here is the angle that is equivalent to the altitude to the altitude, to the latitude of the observer. So this right here is just the latitude. So whatever the number of degrees this is the latitude. So if I'm near the pole of the moon, then this gets bigger and bigger, right? It approaches 90. So if I'm at like 80 degrees north of the lunar equator, then I would have a maximum altitude of the sun that could be something like this, right? So the sun would only reach this height, and it would reach this height, every day. That means that the sunlight would come in at that steep angle, right? In the sense of, I guess, or low angle, depending on how you describe it. So like not from overhead, and you'd have a big shadow. And that shadow would just be there all the time. At night, there's no light, and during the lunar day, it would just always be the same shadow. So that means that light never gets here. You just have a permanent lack of light on these these sides of craters. Right? So here's a lower angle sun because of a higher latitude location for the crater. If the crater's shallow, then kind of extend. You can change the shape of it, right? But it makes it smaller region for a shallow crater. But for a real deep crater, you can have this almost the entire bottom of the crater just permanently in shadow. And so this has some real interesting effects, right? And then it gets into the trigonometry, which you're not responsible for. But let's leave this one up. Well, I mentioned that this has caused a lot of interest in some of these polar equators because some satellite images, and these satellites of the moon, because there are, some, they're always temporary, but we put satellites around the moon, us and other countries, to space agencies in general, and humans in general, I suppose. And when they take these pictures, right, and they fly over the poles, they've looked down into some of these deep craters near the poles, and they're pretty sure there's ice down there because you got this crater that was made 2 billion years ago, and it's there was like an opportunity for liquid water to sort of kind of probably either like be deposited from a comet or maybe like during, like still be left over from differentiation. But point being is that it's never just vaporized into space, which any other ice on the surface of the moon would, because that total lack of atmospheric pressure and total exposure to all the high energy photons from the sun and elsewhere. But down here, there's protection from all that. So the ice is able to remain, indefinitely and has for billions of years. And that means that it could be a reserve of drinking water for a base, or fuel for future, jumping off points of space exploration. The Shackleton crater is one that is really of a lot of interest currently on the moon, as some space agencies are turning their attention back to the moon after a long hiatus since the last time that the moon was in the news, sort of, right? Okay, and like I said, we're skipping over the trigonometry, gets into it more than I hold you responsible for. But second topic, real fast, the origin of the moon. We actually briefly talked about this, that the, how the moon was formed. At least I remember bringing it up. But let's first of all, for the sake of argument, consider some alternate explanations of where the moon came from. And historically, these have all been seriously considered hypotheses of where the moon came from. And one thing that I know I've talked about and what we've seen as a concept question is, in chapter 7, is what is exceptional about the moon? Why does the moon seem to not fit a easy pattern or generalization for the solar system? And it's its large size and relative closeness to Earth. It's got a diameter that's a quarter the size of Earth, and that's just not easily explained for a terrestrial planet to have such a big moon. Okay, so Why do we have such a big moon? Well, maybe it just split off from Earth, right? Maybe when Earth was entirely molten, there was some process that caused like a fission of these two parts. I haven't looked too much into this hypothesis, but maybe it had something to do with rotation. Maybe scientists have supposed in the past that that the two halves were sort of rotating fast enough that the in the reference frame the centrifugal force was able to pull them apart. But for whatever reason, we just split apart at birth, so to speak. The other, another of the fourth hypotheses is that the moon is a sister body. It was formed around the Earth just as the planets did around the sun by accretion. This isn't too outlandish. There are plenty of moons that form this way, but only around the Jovian planets. Almost all of the big Jovian moons, so Titan on Saturn and Io, Ganymede, Callisto, and Europa, although not quite in that order. Also, those five moons between the two planets all formed via accretion between, exactly this way, almost like there was just a bunch of extra matter rotating around those gas giants, and they event that matter coalesced or accreted into moons. All right, so maybe that's where our moon came from, as people have thought in the past. I keep saying the past because you'll see that these hypotheses have since been rejected, at least by the vast majority of the scientific community. Another theory is that the moon was captured. Earth's gravity caught the moon. This also is totally believable because we're pretty sure that Triton orbiting around Neptune is a captured, rather large moon. And lots of the small moons, including the two moons that orbit Mars, are almost certainly captured asteroids. So you have lots of evidence of captured moons. So is that where our moon came from? But it's so big, right? And that makes that less likely because that's a much harder thing to explain to have such a, really strong gravitational, reaction. How could that have happened, stably, so to speak? And then the hypothesis that has basically become a theory, right? It's been upgraded to a theory, the giant impact. The moon coalesced after a giant impact. So kind of, accretion, but not accretion during formation, but a later stage accretion. So fully formed Earth, giant impact, big disruption to Earth, big, large percentage of Earth's matter getting thrown into space, and a lot of it never getting pulled back down to Earth, but instead staying in orbit and coalescing. So this is kind of our picture, a Mars of the giant impact, a Mars-sized impactor, right? The thing that does the impacting, threw material off of Earth's surface, right? After it hit, that would be the impact, right? The throw leads to the disk, and the disk, coalesced into the moon. And it's gravity that does that coalescing, right? Pulls things together, right? Gradual process. And so then that's where we think our moon came from. All right. And there are supporting evidence to this theory, but it's still under exploration, study, and it's quite fascinating because trying to confirm that maybe we never will, but it's there's some neat ideas about how it kind of happened, and there's this whole kind of gradual. The moon was much closer, so if you go back, you know, not to like dinosaurs, but really early life, the moon would have been much closer, and the tides would have been incredible. If you go back like a billion years, and then it's just gotten less dramatic over time, but still a big moon. So, rundown of exploration. This isn't my kind of area of expertise. So, I don't follow too much about the history of say like NASA exploration, but they point out that in the 60s there was the Saturn tests. I definitely heard of them. Then it led to Gemini. Um, I think so. Saturn was testing like the rocket, just finding out you know how to launch something fast enough that it wouldn't just go into orbit, but actually go out of orbit and then be able to slingshot around the moon. Because before this, that this isn't too far after, Sputnik, right? And the first, orbital events, right? The first times we were even going to orbit around Earth. So it was a whole new idea to do a space mission that wasn't just low Earth orbit. But I'm not sure how the Gemini were separate, but maybe they started sending people up. Um, I don't think the Gemini missions actually went around the moon. Um, I had thought so, but I think that actually came with Apollo. So the Apollo missions are obviously the most famous ones, but the first few didn't land on the moon. They just went around it. And we can kind of maybe see that here with Apollo 7. So where it shows the kind of the human occupied pod, which if TV shows have not led me astray, I think had three people inside. And so some of these Apollo missions practice the whole idea of sending people all the way out, having them slingshot around the back of the moon, as in the side that we can't see from the surface of Earth, and then safely return home. And that's kind of this figure-8 path sort of implied here too, right? In terms of what they would take. The probe would enter Earth's orbit, fire some thrusters, go out, slingshot around the moon, come back, decelerate, go back to the atmosphere, not burn up, open up your parachutes, land in the ocean. All right. So then we get to a successful moon landing. So after they tested that whole going around the backside, which I do know that was a big deal because we'd never sent anything that far away from Earth because it's much further. I mean, the difference cannot be stressed enough. And I got a number for you. So low Earth orbit is about 400 kilometers up. That's not very far. I mean, 400 kilometers is like not even all the way to LA. And that's where most satellites are, just directly overhead, and a few of them are higher, but not much higher. And the moon, on the other hand, is so it's 60 Earth radii, which is 6,000. So it's 360,000 kilometers. So it's the difference between 400 kilometers and 360,000. You know, that's the difference between sending something to orbit and sending it to the moon. So it was a lot of time in space. It was going way out into space and not knowing like what deep space is like, like is the radiation like way stronger out there, are people going to be okay? And so, obviously a lot of unanswered questions and interesting fundamental science. But then they it worked, they got people to go all that way and come back and even do that whole slingshot. So then they landed, which wasn't a big change because they kind of were prepared to land. And it's easy to land and take off on the moon because the gravity is so low. Taking off of Earth, you need these big giant rockets. I said this isn't my area of expertise, but I know a little some things, right? And you need a lot of energy. Huge amount of energy to get out of what we call the gravity well of Earth. That's it because we're down at the bottom of a well in the sense of the gravitational influence, which is a great place to be because there's an atmosphere down here. But got to get in space. Just it's hard in terms of it's extremely energetically expensive and also literally expensive because that fuel is not cheap. But landing on the moon, the gravity is just so low, that no atmosphere, so you don't have to worry about all that air resistance. So quite easy to both land and take off, at least comparatively. A world difference. Of course, Apollo 13 is famous because it didn't make it. They had to abort and barely made it back home alive. All right. We've seen the movie, right? Tom Hanks. And then the 14 and 15. So we just kind of continue. And then I don't know if you've sort of heard this sort of summary about the later Apollo missions. They just kind of petered out. They kept going, but they weren't really doing they were doing some interesting science, but they also never sent a scientist. They never sent a single scientist to the moon. And so they thought about it, but at that point, they lost their funding. So they kind of like I feel like they missed the mark there a little bit. I think they probably should have transitioned over to like, some hard science that they could at least, pitch to Congress in terms of its usefulness, application, and then also get the support of the, academic community. But they didn't, and so they just completely lost all support and lost funding by 1974. Well, they lost in 73, and so there would be none of it for 74, which is what this quote points out. And I love this question just because it's totally just open-ended. So adjusted for inflation, the whole, NASA moon missions cost 283 billion over 13 years. Was it worth it? What do you think? Was it worth 283 billion? Yeah. So yeah, like it it's hard to say, I like yeah, we got some yeah. It's like some people kind of have a gut reaction to say yeah, because it's just, like come on, we got to do it, and then other people are like, well, there's all these things that we need to spend money on Earth, That's a lot of money, right? It could be a lot of schools and, like food programs or whatever, help for the homeless. But would it have been? Probably not, I don't know, but that's not really a fair comparison, I think, if you if you learn your logical fallacies and debate, that might fall apart. But still, all that aside, it's just interesting to think about, and then going forward, right? Maybe maybe the moon is just sort of like the wrong place to go because there's not much to offer. But then again, space is always going to be hard and expensive and have few returns, but eventually it might have returns, you know? Or we could just ignore going to space altogether and just agree that, humanity just, we can study it. That's great, but we should just never go there. Like that's not a totally outrageous argument, but then of course we want to, right? We always want to spread out and, see new things. Okay. So fun stuff to think about. So as promised, this bit quickly mentions the idea that the moon is tidally locked. So let me show you that slide real fast as we run through our last 5 minutes here. I know the other day I didn't use the last 5 minutes, but today I will. If I can get the Zoom to work, come on. There we go. There. So tidal locking, if you remember, the moon is a pumpkin. So if you have a pumpkin and you look at the face of the pumpkin, and so this picture I feel like is kind of misleading, but I think I've made sense of it. So because look, the face in the diagram is facing away from the head, and here the head is Earth. Remember, okay, the head represents Earth. So the person can't see the face. So here, either like this is just like showing you what the face would look like if you could see it, because the light does look like it's behind it, um, light being the sun, but obviously the Earth can't see it. So that's what's weird about it. But anyway, the face is over here, facing away from the Earth. If you could see it, it'd look like that. Okay. Unless it's glowing through it. Is that what it's supposed to be? Maybe that's it. It's carved, and we're just seeing, yeah, I think I just figured it out. Okay. Because it's a carving. So this is literally the light that's going into the hollow pumpkin and then partially coming out of it, which is why it looks so faint. Okay. So that's the new moon, apparently. The new moon is the face of a pumpkin shining through the pumpkin itself. Despite that, and unlike the pumpkin analogy doesn't work that well here because we can't see the far side of the moon, the so-called dark side of the moon. And unlike the face of the pumpkin, it doesn't shine through the interior of the moon. It's just cannot be seen by us unless we go into space. That's the only way, so those missions, right? That's the first time anyone taken a photograph of the dark side of the moon and they started to map it. It's a lot like the near side of the moon. But it's not dark, as we talked about before. Both sides of the moon have a day-night cycle that's identical. There's that. It's just that because of this tidal locking, because of the way it rotates, that face always faces away from us. So the carved side of the pumpkin, just like the so-called dark side of the moon, never faces Earth. And that's simply because the rate of rotation is equal to the orbital rate. So the time it takes for the moon to spin on its own axis, say 29 days approximately, is equal to the time it takes the moon to revolve or orbit around Earth. There you go. Since those two are equal, we never see one side of it. And the fact they're equal is a natural consequence of tidal locking, which is a loss of energy to tides, hence the name tidal. And the locking refers to the fact that that this state is a low energy state that any two-body system will approach. And so the moon, from when it was first created with that giant impact, assuming that theory is correct, then it started approaching tidal locking from day one, but it didn't get there until about 1 billion years later. But has still for the last 2.5 billion years, it has been tidally locked, and it remains so. And now the moon Earth system is approaching the even lower energy state of double tidal locking, which is what, for example, Pluto and Charon are in, which is Pluto and its moon Charon. Charon is almost the size of Pluto, which is why in the history of the solar system, those two bodies have been able to reach double tidal locking. And what double tidal locking is when the one more rate equals the other two. So double tidal locking is where the revolution rate of the moon equals the rotation rate of the moon equals the rotation rate of the planet, the thing that's being orbited. Okay? So, in other words, at some point, our day will be so long that it will equal the month, as you know, which means it will equal the revolution of the moon. And at that point, it'll be even longer than it currently is. To reach double tidal locking, the the moon will have an orbital period of 44 days, which means that our day-night cycle will be 22 hours of light and 22 hours of darkness, which would not work at all for any life forms that currently live on Earth. But luckily, the sun will have destroyed Earth well before that ever would have happened. So actually, we'll never reach that state. It would take, I think, another like 19 billion years to reach that state. So unless we get flung out of the solar system and avoid being consumed by the red giant sun that our sun will become in some 5 billion years from now, we'll never have to worry about super long days and you know, the state of being doubly tidally locked with our own moon. But our days are getting longer, marginally, especially within, human lifespan timeframes. But, if you look over millions of years, our Earth days just get gradually longer and longer, and the moon gets further and further away. All right, so that is where we will stop. We won't get to Mercury just yet. So I'll stick with, I'm still going to put on the test, just a little bit of a squeeze, and we'll just have the quiz a little bit later. So we do the thing that I do sometimes where I'm not quite finished, but you are responsible to read about Mercury. Look over these slides, watch some of the videos, read the sections in the book on Mercury. Okay, you have lots of places to look, but we will talk about it as a class for 30, 40 minutes on Monday, and then take a test on, not test, a quiz on this whole chapter. Sound good?
Yes, I have a question. I saw that the test was open on July 1st. Never mind. Never mind. I was going to say I'm going to be out of town on the 3rd, but never mind. That doesn't correlate. Never mind.
Okay. Yeah. No, opens on the 30th, closes on the end of the first. Yeah. Cool. I'm glad there's no conflict. Awesome. Awesome. All right. Goodbye, everybody. Have a great rest of your morning. I will see you next week.
Thank you.
Bye-bye.
Thank
Have a
you.
nice
Bye
day.
bye.
Thank
you.
you. Bye.
You.